Hello, good morning. Am I audible?
Yes, sir.
Yes. Okay, good morning and welcome to lecture on advanced power electronics. Last time we discussed single phase, a full wave, full control converter. So last time we discussed this single phase, full wave, full control converter. It has two operating modes. One is rectifier mode, a first quadrant operation, and another is inverter mode, which will be a fourth quadrant operation. In case of rectifier mode, we are considering the RL load. Then we have seen that whatever may be the alpha, our source current is the square wave. So source current of single phase full wave full control converter is the square wave. And we have seen that the power factor of this case will be depending upon the alpha, and power factor of single phase full wave full control converter is given by 2 root 2 by pi a cos of alpha. Whereas in case of inverter mode, we require our load should be RLE with the proper polarity of battery, then firing angle should be greater than 90 degrees. We should have a sufficient inductance so that continuous conduction will be achieved, and we require a battery at the output side such a way that the battery will support the current. And under that condition, our alpha is greater than 90 degrees. We have seen the output voltage waveform. So this waveform we have shown output voltage. Let us assume the alpha may be approximately 120 degrees, maybe slightly greater than, but let us assume it is a 120 degrees. This is the output voltage waveform for a particular alpha equal to 120 degrees. So output average output voltage is negative, but here also devices T1 T2 conducts for a period of 180 degrees, and a T3 T4 will also conduct for a period of 180 degrees, and our DC current here, it is a smooth and ripple free. So this is our DC current, that is a smooth and ripple free, and hence each device conducts for a period of 180 degrees. Here also our current is the square wave. So very important thing is that our source current of the full control converter is the square wave. After that, we discuss the three-phase diode bridge. And in case of three-phase diode bridge, we have seen that D1, D3, D5, out of that one device will be always on, whereas lower group you can call as D4, D6, D2. Out of that one device will always on. So this 360 period is shared by these three devices. That's why each device is conducting for a period of 120 degrees. D1 is conducting for 120 degrees. D4 is conducting for 120 degrees. And we have seen that our output voltage waveform is the upper envelope. Output voltage waveform is the upper envelope. So ripple content will be very less, and we have seen it here. That is a VAB. If you see this, I'm showing is the VAB, where A is maximum positive and B is negative. So A is maximum positive, so I'll mark it here. A is maximum positive and B is maximum negative. So here we have seen that A is positive, means our D1 will be forward bias. A is positive, and B is negative, means D6 will be a forward bias. So here a first period VAB. Here if you see it, 1 and 6 will conduct, or I will write it here 1 and 6, device number 1 and 6 will conduct. Okay, if you have a AC, what is meaning of AC? Next 60 degrees AC means A is positive and C is negative. So A is positive, but now C becomes a negative. When C becomes negative, we have seen that which device will be forward bias. C is negative means our D2 will be forward bias and D1 will be a forward bias. A is positive. So A is positive. So here this period we are having a D1 and D2. So this period we are having a D1 and D2. So this will be the case. We have shown it here. Similarly, it is a BC. You can also try out. B is positive and C is negative. If you go back, B is positive now here. B is positive. Sorry, B is positive. So this is a B is positive and C is negative. So this is the negative. So D2, D3. B is positive means D3. So if you just write it here, next is 3 and 4. 2 and 3, sorry. 2 and 3. Then next is 3 and 4. Okay, so this will be a 3 and 4. I am each 60 degrees. We can just write down this. And whenever 1 is on means our diode 1 is on. So 1 is on means the D1 is on. So this 120 degrees diode D1 is on. Similarly 3 and 4. Here 4 and 5. Next is the 4 and 5. So here 4 is conducting means our diode D4 is conducting here. And now when D1 conducts, our source current is positive. D1 conducts, source current is, sorry, D1 conducts, source current is positive. And D4 conducts, our source current is negative. So the source current of diode bridge is the a Cauchy square wave. Or here we have shown, this is our D1 is conducting for 120 degrees. D4 is conducting for 120 degrees. So source current will be a Cauchy square wave. So in case of diode bridge, each device conducts for a period of 120 degrees and DC ripple is less than 5%. You can find out from finding the average value and the RMS value. Each device conducts for 120 degrees, but the pair D1, D2, D2, D3, each pair is conducting for a period of 60 degrees, and we have shown it sequentially. 6, 1 is conducting particularly for this period, then 1, 2, then you can write a 2, 3, then we can go for 3, 4, 4, 5, 5, 6, and the so on. And now our interest is, so this was where I discuss about the R load. So where R load, our current is having some ripple. Okay. Whereas in case of RL load, our DC current will be a smooth and ripple free. So our IDC is smooth and ripple free. And here we have shown it here, VAB. A is positive, B is negative, and AC. VAC. Similarly, you write others. And here we have seen that D1 is conducting for 120 degrees. Similarly, after that, D3 is conducting for 120 degrees and D5. Similar, we can write. So here D1 is conducting for 120 degrees. So positive current for 120 degrees. D4 is conducting for 120 degrees. So negative current for 120 degrees. So this is the case for A phase. Similarly, we can go for other. So here we can conclude that diode bridge for R load as well as RL load, current will be a Cauchy square wave. So this waveform of current you can call as a Cauchy square waveform. And now our interest is we find out the THD for the Cauchy square wave waveform, and we are already knowing the expression. So for finding out the THD, what is the procedure we have to follow? We find out first the RMS value of waveform, square mean root value of the waveform. So IRMS you can call as I, or I will call it here as a IRMS value. First thing is you find out the RMS value. What is next thing? You find out the I1 RMS. You find out the I1 RMS. I1 RMS means RMS value of a fundamental current. Once you know the IRMS, you know the I1 RMS, then you can find out the harmonic current RMS value, IHRMS. IHRMS. So we want to find out three values, but out of that, first we find out from the waveform, we can find out RMS value. How to find out RMS value? First you take the square of the waveform. then take the mean of the waveform, and then take the root of the waveform. Square mean root. Okay, in that fashion we find out the RMS value. And now we are using the expression AN, peak amplitude of nth harmonic, and that expression is 8 by 2 pi 0 to pi by 2 f theta cos n theta d theta. And here for that we want to have a quarter wave symmetry. Okay, we want to have a quarter wave symmetry, so we shift the 0, and from that, solving this, we will get the value of I1 RMS. We can get the RMS, and using this expression, whatever we are having, I RMS square will be I1 RMS square plus IH RMS square. With that, once we know the I, we know the I1, we find out IH, and our THD percentage THD will be IH by I1 into 100. So this procedure we are repeating here. Okay. So this is our a particularly source current of three-phase diode bridge. We are taking as the RL load. It is the Cauchy square wave. You see, it will be the Cauchy square wave source current, 120 degrees positive current, constant value equal to IDC. For this waveform, we want to find out the expression for AN. And for getting our expression for AN is 8 by 2 pi 0 to pi by 2 f theta cos n theta d theta. So this is our expression. Whereas here we have seen that we shift the origin at the center of the pulse. So now our waveform, we rewrite this x-axis 0 at the center, then 60 degrees, then 90 degrees we write. So we want to integrate only a function up to 0 to 90. Whereas we are having function is present up to 0 to 60. And from 60 to 90 is 0. So we can just change it here. Integration limits will be 0 to pi by 3, because up to pi by 3 our function is present, and up to pi by 3 our value is IDC cos of n theta d theta. Now we integrate this, and substituting values will get the expression we have done last time. So it is 4 n pi, 4 divided by n pi into IDC into sine of n pi by 3. And now putting n equal to 1, by putting here, by putting n equal to 1. So we put a n equal to 1. So put n equal to 1, this n equal to 1. You will get the A1. What is meaning of A1? A1 is a peak amplitude of a fundamental. So this is our A1, a peak amplitude of fundamental. That is, peak amplitude of fundamental is 2 root 3 by pi IDC. We get, just put n equal to 1, 4 by pi IDC sine of pi by 3. Putting these values, you will get our A1, that is a peak amplitude of fundamental. A1 is peak amplitude of fundamental is 2 root 3 by pi IDC. And now this is the peak amplitude. We want I1, that is RMS value of fundamental. So divided by root 2. So it will be this will be I1 is the RMS value of fundamental component of current. I1 is RMS value of fundamental component of current. It will be root 6 by pi into IDC. So we get this. Now what is RMS value of this waveform? Can you find out? What is IRMS of the Cauchy square wave? IRMS value. What is IRMS value? Anybody quickly can tell us this? How to find out RMS value? So we just square it. So IDC square minus IDC will also become plus IDC square. Then 120 degrees, 120 degrees. Then take the square of the mean of the squared waveform and take the root. So can you find out what will be its value of RMS value? Am I audible?
Yes, sir. Yeah.
So what should be its RMS value?
I naught under root 2 by 3. IDC under root 2 by 3.
Okay. So square root of 2 by 3 into 2 by 3 into IDC. Is it right? Okay. So this will be our value of IDC. So square root of 2 by 3 into IDC. So we know the RMS value. We know the I1. I1 is this root 6 by pi IDC. This is this. then you find out IH harmonic current, and then so here we find out. So this is our IRMS value, square root of 2 by 3 IDC, that is IRMS. And so we find out IH with this formula. IH will be a square root of I square minus I1 square. And IH will be just putting the value 2/3 IDC square. Okay, so I1 square is square root of 2 by 3 IDC. So we'll get this square root, and then I1 square root of that. You simplify that, IH will come out to be a 0.242 IDC. Once we know the IH, we know the I1, multiplied by 100, we get the THD. So the total harmonic distortion of the quasi square wave current is almost 31.08%. 31.08%. So is it clear how to find out the THD, particularly for the quasi square wave current? And this quasi square wave current is the source current of diode bridge. So any question on this? Any doubt how to find out the THD of the quasi square wave? How to find out the THD of the quasi square wave? Any question?
No, sir. No questions.
Okay, so let us go for, and now we done, last time we also discussed this we can find out with a MATLAB simulation. And this is a particular, we have seen, this will be our source current waveform. We simulate the diode bridge with RL load, and this is our source current of one phase. It is a quasi square wave, positive for 120, negative for 120. In between 60 degrees, we are having a zero value. And then we use the FFT analysis of MATLAB. We are knowing we can use the power GUI. We find out the FFT analysis of this waveform, and FFT analysis we have shown. Particularly, it contains the harmonics, that is a 6m plus minus 1. It contains the harmonics of 6m plus minus. M is any integer, 0, 1, 2, 3. So what harmonics are present here? So first is fundamental. When m equal to 0, we are in fundamental. Then m equal to 1. So 6. Okay. So it will be a 6 minus 1, 5, 6 plus 1, 7. Then we are having 11th and the 13th. Okay, so these are the harmonics present. So what is the harmonic spectrum? 6m plus 1 and a 6m minus 1. And we have find out first 4 harmonics, putting m equal to 1 and m equal to 2. You can put m equal to 3, so 17 and 19 and so on. You can just make the list of the harmonics. So what is our concluding point here? The harmonics, what are all odd harmonics except triplen harmonics? So we can say that this quasi square wave contains all odd harmonics except triplen harmonics. Except triplen means 3, 6, 9, 12. These harmonics are absent. Triplen harmonics are absent, and odd harmonics except triplen, that will be called as 6m plus minus 1. And the harmonic will be, this is the fundamental if you see it here. Then fifth is having a 250 Hz frequency. Fifth, then we are in 7th, then we are in 11th, 13th, and so on. And we find out the THD, particularly this will be 30.4%. Okay, there will be a slight variation. So here our calculated value comes out to be a 31.08, but here it will come as a 30.4. So approximately we are having 31% THD in the of the source current of the diode bridge. Now let us consider we are having a diode bridge. Earlier we consider R and RL. Now we are considering case here we are having a capacitor is used. Now here we are using a capacitor. So this is our a capacitor is used and a load. And now the voltage across the capacitor will be approximately constant, because already ripple is less in case of resistive load. We have seen that ripple is upper envelope. Ripple is almost less, and if you use a capacitor, again we can get the output voltage will be across the capacitor will be smooth DC, and this output voltage across the capacitor will be a smooth DC. We represent this dotted line. I am just making it here. So this will be our output voltage across the capacitor. So it is average of this whatever we are having. So it will be a smooth DC voltage appearing across the capacitor. And now because of this capacitor voltage, we have seen that, let us assume that here VAB and VAC, where which devices, VAB, which devices are conducting A and B. So it will be a 6 and 1. So it will device number 6 and device number 1 is conducting. Here device number 1 and 2 is conducting. Here device number 2 and 3 is conducting. Here 3 and 4 is conducting. And this 5 and 6 will conduct. Sorry, 3, 4, 4, 5. 4 and 5 will conduct. And this will be a 5 and 6. So this will be a 5 and 6. So we are having a 6 pulses. So it is called as 6 pulse rectifier. And here we have seen that here which devices are conducting, D1 and D6 are conducting. But they will conduct when our instantaneous voltage is higher than this. So this particularly D1 and D6 will conduct. D1 and D6 will conduct only when instantaneous voltage is higher. So here this period we have seen that devices D1 and D6 will conduct. Here in this period we have seen that D1 and D2 will conduct. Here D2 and D3. Similarly here D3 and D4. Here it will be a D4 and D5. So what is our conclusion here? D1 and D6 are conducting less than 60 degrees. D1, each device is conducting, pair of devices is conducting less than 60 degrees. Pair of devices means D1 and D2 will conduct less than 60 degrees. D3, D4 will conduct less than 60 degrees. And when they are conducting less than 60 degrees means total D1 is conducting less than 120 degrees. And here in between that no device is conducting. So D1 and D6 is conducting. So one is conducting, and for that our period will be, current will be like this. In between that no D1 is conducting, D6 is not conducting. And next we are having is a D1 and D2 will conduct. So this will be our nature of source current. We can obtain similarly here a D4 is conducting, so source current will be the negative. So how is our source current now? Source current is we are having the 2 positive pulses and the 2 negative pulses. That will be our waveform of the source current of the diode bridge when we are having a RC parallel combination. Here we are having a RC parallel combination, and in that case device pairs D1, D2, D2, D3 will conduct less than 60 degrees, and because of that our source current will be 2 positive pulses and the 2 negative pulses. So that type of source current we can obtain. So capacitor voltage conduction period of device is reduced because device will reverse bias some period because their instantaneous voltage is less than the capacitor voltage. So here if you get this we are having 2 positive pulses in the positive half cycle, 2 negative pulses in the negative half cycle of the input, and here you find out the THD for this case, and the harmonic spectrum for this waveform is also a 6m plus minus 1. Okay, the harmonic spectrum will be same as 6m plus minus 1, but only thing is that our THD will be higher. So this is the change in the particularly source current waveform, particularly drives. In case of induction motor drives, when we are having front end as a diode bridge rectifier and then capacitor, then definitely this will be a source current of variable speed drive. Variable speed induction motor drive, the source current is not sinusoidal. This is the nature of source current of AC drive. So AC drive will take a current, this type of current from the supply, because at the front end it is having a three-phase diode bridge, then it is having a filter capacitor, and because of that, our three-phase variable frequency induction motor drive will take this type of nature of current, where our whereas we have seen that our harmonic spectrum is having a 6M plus minus 1. But the THD will be higher. Now for the same, we have done diode bridge with RC parallel load. We done the simulation and we find out the here THD is with the help of MATLAB we find out THD, and this THD is around 167.94%. So THD of the source current is very high. So this is the case for a diode bridge. Now we can go for any question. What is our conclusion? Anybody? What is our conclusion of the diode bridge? A source current of diode bridge is, in plain way, we can say that a source current of diode bridge is non-sinusoidal. It takes the Cauchy square wave current, and this Cauchy square wave current THD is around 30.4% or 31% when it is working with R and RL load. Whereas when it works with RC load, the harmonic spectrum remains same, but the THD will increase, and our source current will have a 2 positive current spikes and 2 negative current spike. And we simulate this with the help of MATLAB simulation, and we find out that THD is around 167.49%. So any question? Am I audible? Any doubt?
No, sir, no questions.
Yes, any question?
No, sir.
Okay, I am expecting questions and doubts. Okay, so you should raise the questions as the doubt, that will be useful for your understanding. Now let us go for our 6-pulse converter. So when alpha equal to 0, everybody knows when for a 6-pulse converter alpha will be equal to 0, it means that our thyristor converter will become like a diode bridge. Okay, so and we have discussed that for a diode bridge our source current is Cauchy square wave. So for 6-pulse converter alpha equal to 0, what is our comment? For 6-pulse converter with alpha equal to 0, again we say that our source current is a Cauchy square wave. So we have shown the circuit diagram for a 6-pulse converter. This is 3-phase supply, and we are having the thyristors T1, T2, T3, T4, T5, T6. This is the load you can represent as a constant. We are having a DC value, constant DC value. We represent it as a current source. Okay. So here, particularly we have seen that what is the range of alpha? What will be range of alpha for this converter? Anybody? What is the range of firing angle alpha for 6-pulse converter? The 6-pulse converter we can also call as a 3-phase full wave, a full control converter. 6-pulse converter, another name is 3-phase full wave, a full control converter. What is the range of firing angle alpha? What is the range of firing angle alpha?
Two ranges,
it
like
has
for
having
0 to 120 continuous, and after that discontinuous.
Okay, so here I will just, okay, your answer is appreciable. Okay, we'll correct your answer. That, okay, we are having, depending upon the load, for our load, if we are having only a resistive type load, okay, only we are having a resistive type load, then our range of alpha is 0 to 120 degrees. Okay, so for particularly for resistive load, when load is resistive, our range of alpha is 0 to 120 degrees. RL with the RLE or 2-quadrant operation, for RL and RLE you can say, okay, our range is 0 to 180 degrees. Our range is 0 to 180 degrees. Okay, so this is the case we are having a range of alpha 0 to 120 degrees for resistive load. Out of that, 0 to 60 degrees continuous conduction, and 60 to 120 it is a discontinuous conduction. So 60 to 120 it is a discontinuous conduction. So in case of resistive load, up to 0 to 60 degrees we are having a continuous conduction, and from 60 to 120 it will be discontinuous. But in case of RL load or RLE load, we can say that our alpha is varying from 0 to 90. Again, this full control converter, it works in the two quadrants, rectifier in operation as well as inverter operation. Is it clear? The range of firing angle R load 0 to 120 degrees. Out of that, 0 to 60 is continuous conduction, 60 to 120 is discontinuous conduction. Particularly RLE load, we are calling it as a 0 to 180, and in that case 0 to 90 will be a rectifier operation and 90 to 180 will be inverter operation, provided conditions are satisfied. Provided inverter operation requirement conditions are satisfied, that alpha is greater than 0, we should require a battery in the DC source and sufficient inductance to maintain the current continuous. And now we have shown that all this are particularly RL with continuous conduction or R with continuous conduction and RLE, our device, each device continues 120 degrees. Each device conducts for 120 degrees. T1 conducts for 120 degrees. A T4 conducts for 120 degrees. So what will be our source current? A positive current for 120 degrees and a negative current for 120 degrees. Negative current for 120 degrees. So negative current will be like this from this. So it means that each phase current is a quasi square wave. Here also the phase current of thyristor converter is the quasi square wave. So positive current for 120 degrees and negative current for 120 degrees. So this current, particularly our source current of 6 pulse converter, is also a quasi square wave. This is the getting pulse requirement. So both devices discontinuous conduction. So here 1 and 6 are conducting. So conduction will start here at 1 and 6. So both should be turned on. After that, both will be off because of discontinuous conduction. And again, we have to turn on 1 and 2. So we have to give the pulse to this. Again, 1 and 2 both will off in case of discontinuous conduction. So in case of discontinuous conduction, if you see here, 1 and 6 are on here. So here we have to give the pulses to both, and both the D1 and D6 are T1 and T6 will become off. Again we have to turn on the T1 and T2. So we require 2 pulses at the interval of 60 degrees. Okay, so that the conduction will be maintained, so that switching will be proper in case of discontinuous conduction also. Now this is the output voltage waveform for alpha equal to 30 degrees. How to measure alpha? Alpha is where D1 starts conducting. So this is here we are having crossing of 2, VCB and VAB. VCB and VAB. Where our VAB, this is a conduction of diode starts here. So this is alpha equal to 0 position, particularly for T1. After that, this will be alpha equal to 0 position for T2. This is for T2, I will write it as a 2. This is for 2, this is for 1, then this is for 3, from where we measure the firing angle. And this firing angle is 30 degrees. So this T1 AB, which devices will conduct? VAB, A is positive and B is negative, 1 and 6. So this will be a period where devices conducting are 1 and 6. Okay, next from this 30 degrees, we are having AC. AC means which device will conduct? AC, A is positive means T1, C is negative means T2. So 1 and 2 will conduct this period. Similarly, if you write it here, 6, 1, 1, 2, then we are having a 2, 3. Okay, then we are having 3, 4. 3, 4, then we are having a 4, 5, and then a 5, 6, and then again this is 6, 1. So this instant and this instant is one and same. And so we have seen that here 1 conducts for 120 degrees. So this will be our 1 conducts for T1 conducts for 120 degrees, so positive current. Here T4, if you see it here downwards, the T4 conducts for 120 degrees, so T4 conducts means a negative current, T4 conducts a negative current I am showing, and T1 conducts the positive current. So this will be our wave shape of current. Okay, so here quasi square wave. Now if firing angle shifts, now let us go for alpha equal to 90 degrees. Alpha equal to 90 degrees. So this is our alpha equal to 0 position. This is alpha equal to 0 position for T1. This is the T1. And now we are measuring the alpha is from here to this. This is 90 degrees. Then next 60 degrees it will be on. Next 60 degrees it will be on. So this is alpha equal to 0 position for T1. This is 90 degrees period. So this is alpha equal to 90. And this is the VAB will conduct after this for 60 degrees. So this will be here whatever I marked here, which devices will conduct 1 and here device conducts will be 1 and 6. Here device conduct will be 1 and 6. Device conduction will be 1 and 6. Similarly, here again we write device conduction will be 1 and 2. Here conduction will be a 2 and 3. Then 3 and 4 and so on. So here we have seen that our earlier conduction starts from 30 degrees here to here. Earlier for alpha equal to 30 degrees, this was the conduction. Now alpha equal to 90 degrees, this will be a conduction. But conduction period remains same. It means that the nature of current waveform remains same, but it shifts with respect to voltage. We say that when alpha changes, our wave shape of current will remain same. Now let us go for alpha equal to 150 degrees. Now we are going for inverter operation, and you are knowing what is the essential conditions for inverter operation. So what is this conditions for essential conditions for inverter operation? Can anybody tell what are the essential conditions for full control converter to work in the inverter mode? What are the essential requirements?
Battery voltage must be greater than the.
Okay, battery voltage should be greater than the converter output, but alpha can be controlled so that it can be managed. But one important thing is that battery voltage should be of proper polarity. So we have shown the downward terminal is positive. Okay, upward is negative. Whereas converter rectifier mode, we have seen that upper is positive and lower is negative. But in inverter mode, what is the converter output polarity? Lower is positive, upper is negative, because the polarities of the output voltage are reversed. So here condition is one is alpha should be greater than 90 degrees. That will be first condition for inverter operation. Second is we are having a sufficient inductance, so continuous conduction. So we are having a continuous conduction. That will be another. So we require a sufficient value of inductance, and battery should be of proper polarity. Now here we are going for, this is alpha equal to 0 for a T1. This is the instant crossing of this alpha equal to 0. For T1, this is the instant where alpha is equal to, I am writing it will be 0, T1 equal to, and after that this will be our APE. This is our VAB waveform I am tracing. VAB. This is our VAB. This is the waveform which we are having is the. This is the waveform. I am just putting this notch. Okay, dots. That will be this is the VAB. And which devices will be conducting now? In case of VAB, A is positive 1, B means 6. 1 and 6 are conducting. But from here, what is distance here? This is alpha equal to, this is 60 plus 60, 120 plus 30. And here we have seen that this will be device. 1 and 6 are conducting. After that 60 degrees, which devices will conduct? 1 and 2. After that 2 and 3, so on. And here again each device is conducting for a period of 120 degrees, and so that our current is cos square, but it shifts with respect to voltage, with respect to voltage. So this is we have shown it here again. So we have shown with respect to voltage, and this cos square wave current, this cos square wave current shift with respect to the voltage. As our alpha changes, this waveform will be shift in the forward direction. That will be the what we want to trace. And we see that this cos square wave current is the harmonic spectrum, and we are already discussed the harmonic spectrum is having the harmonics, that is 6m plus minus 1. So harmonics we have written a fifth harmonic, seventh harmonic, 11th, 13th, 17th, 19th, and so on. Fifth harmonic is 1/5, seventh harmonic is 1/7, 11th harmonic is 1 upon 11 times, and the so on. This is the harmonic spectrum. And now here we have just shown it various alpha. So what you observe, we have gone it here. The cases of alpha is almost 6 alpha cases. We have shown the 6 alpha cases. So RL load 3-phase full control converter with RL load, and we are having alpha. Alpha is 0 degrees, alpha is 30 degrees, alpha 60, alpha 90. So we are having the various cases: alpha 0, alpha 30, alpha 60, alpha 90, alpha 120, and alpha 150. So these are the cases we are having. The 6 cases we have considered here, and these 6 cases, if you see here, our source current, whatever may be alpha, very important point, whatever may be alpha, the source current of diode bridge with RL load is cos square wave. The wave shape of current is not changing, and as the wave shape of current is not changing, harmonic spectrum remains same. With number of harmonics, that what we are having 6m plus minus 1, that harmonic spectrum will remain same. There is no change in the harmonics, whatever may be our alpha, either 0, 30, 90, whatever it may be, we are having this. So this we have shown the phase voltage. So this sinusoidal waveform is the phase voltage VAN. We have shown all the cases, we have shown the VAN at same. And with respect to that, if you change the alpha, how our current will shift. So here fundamental component, if you see here, dotted component will be in phase with voltage. And this is the cos square wave current if you observe it here. Now, whenever alpha is 30 degrees, means this cos square wave current shift by an angle alpha. So here if you see that as our alpha increases, this current will lag more and more. Current will lag more and more. And this is the, we have shown the VAN is the sinusoidal voltage, and IA1, that is a fundamental component of current, that will be in phase with this. When alpha is 0, both they will be in phase, voltage and current. As alpha is 30 degrees, the fundamental component will shift by an angle of 30 degrees. Here alpha is 60 degrees, then fundamental component will shift by an angle of 60 degrees. Similar case for 90, 120 and the 150. And 180 degrees it will be out of phase. So fundamental component of source current, whatever dotted we have shown it here, cos square wave dotted of that will lag the voltage by an angle alpha. And we have seen that this converter always works on the lagging power factor, and this converter works on the lagging power factor, so it requires a lagging reactive power. And power factor of this 6 pulse converter is given by 3 by pi cos of alpha. Power factor is given by, and our output DC voltage VDC, VO output VDC, in this case it will be given by VDC. What is the formula, can you recall? Thrice VML by pi, thrice VML by pi cos of alpha, thrice VML by pi a cos of alpha. That will be our cos of alpha. That will be our expression for output voltage. VML means M stands for peak value, L stands for line. So peak value of line voltage, VML. This VML stands for peak value of line voltage. Thrice VML by pi cos of alpha, that will be expression for output voltage. Okay, as alpha 90 output voltage, average output voltage will be a 0. Alpha greater than 90 degrees, our output voltage is negative. So that will thrice VML by cos of alpha, that will be expression for average DC output voltage. And power factor of this particular 6 pulse converter is given by 3 by pi a cos of alpha. So what is our conclusion? A 6 pulse converter takes a quasi square wave current from the supply. THD of the source current is around 31%, and it takes the reactive power. Power factor of this converter is given by 3 by pi cos of alpha. Now this is the waveform for R load. We have seen that R load, what is the range of alpha? We have just discussed. What is the range of alpha? Our converter is having just a resistive load. What is the range of alpha for R load? Anybody?
0 to 60 degrees.
0 to
60 degrees, sir.
For
R load.
only 0 to 60?
Firing angle, yes, sir, 0 to 60 for continuous
Just
conduction.
go back to the slide where we discussed this. So what we have shown it here for R load, what is the range of alpha?
If we want continuous conduction, sir, that it must
Okay,
be
0 to 60 is continuous and 60 to 120 is
discontinuous.
So this is the extreme case we have shown alpha equal to 60 degree. It is just continuous. Alpha is 60 degree. We have shown is a just continuous. So alpha equal to 60 degree. We just shown the continuous condition. And what is the range alpha here? 0 to 120 degrees. At 120 degrees, our output voltage will be 0 for a resistive load. Okay, and this is just continuous. This is the voltage waveform, and only a load is resistive, so current will be the same as that of voltage. So this will be our source current, not a 120 degrees ripple free current, but here the current wave shape is like this. So this is the 2 pulses of positive current. It is contained 2 pulses of the negative current. This is the nature of wave shape of the THD remains same, but THD will be higher. When you see it here, when you get the alpha greater than 60 degrees, this is our crossing point. Here it is alpha equal to 0 position for T1. This is the 0 position for T1. And then we are having a 90 degrees. So this 60. So this is a 60 plus this is 30. So this is 90 degrees, and 90 to 120 it will conduct. So this will be our 6 pulses of output. What we are getting it here. This will be our output voltage waveform, 6 small pulses in the period of 2 pi. And this is a 1 6, and it's a 1 and 2. So this will be our input source current, 2 positive pulses and the 2 negative pulses. So that will be a wave shape of current, and we find out PhD for this. This is our current waveform for alpha equal to 90 degrees for resistive load. And this is the current waveform. If you see it here, this will be our current waveform. So this is our current waveform. 2 pulses at the positive and 2 pulses at the negative. And THD, where harmonic spectrum remains same. Harmonic spectrum remains same. But now if you see here, THD will be a greater than 112%. So THD is high. Less than 60 degrees, we are having continuous conduction, and discontinuous conduction, alpha should be greater than 60 degrees, 60 to 120. So this case we can summarize. We are just reviewed the rectifiers and converters within the 3 hours. From our perspective of our major intention is on a source current. Major intention is on the source current, and from this we come to a conclusion. It requires a reactive power because it always works at the lagging power factor. Converter, this thyristorized converter diode bridge never works at leading power factor or the unity power factor. Okay, they will always works with the lagging power factor, so that they will take the reactive power from the supply. Though inverter is working, though the control converter is working in inverter mode, or the rectifier mode, in both modes it takes the reactive power from the supply. Also it takes a non-sinusoidal current. Also it takes the non-sinusoidal current from the source. Also it takes the non-sinusoidal current from the source, and hence we say that it injects the harmonics. It injects the harmonics, and we have to compensate that. And now, so we have to, this is the problem. So what is our conclusion of last three lectures? Can anybody conclude in one or two lines? What will be our conclusion regarding the last three lectures? What we were discussing about? Anybody quickly? Hello?
Output voltage and the source current.
Once again you tell.
So output voltage from all the like configuration, like three bridge converter and controlled and uncontrolled converter, along with the calculation of its source current value.
Okay. So we revise all these converters, not all, but single phase full control and three phase full control converter. These two full control converters we revised. But our main focus is on the source current of the single phase diode bridge, single phase full control converter, three phase diode bridge, and three phase full control converter. Our main focus is on a source current. Main focus is on the source current and the reactive power. And what is our conclusion? A converter always works on the lagging power factor. When we are having very poor power factor, at what alpha our power factor is very poor? At what alpha our power factor is very poor for full control converter?
90 degrees.
So 90 degrees, our converter will work as a pure inductor. It will work like a pure inductor, because at alpha equal to 90 degrees, whatever power it takes only reactive power. So that is a converter takes the reactive power. That is a drawback. Why it is a drawback? Because we have seen that with the help, when you take the reactive power, and when you take the reactive power from the grid, you say that the generator, a transmission and distribution, all these cases, a generator efficiency will decrease with power factor, lower power factor. Transformer efficiency also decreases with power factor. So efficiency depends upon power factor, because losses will not depend upon the active power. Losses will depend upon the total current. And as power factor is lower, current will be more, but active power will be less. So that interest is that every equipment we want that it should operate at unity power factor, so that it will give a maximum active power with minimum current, and losses will be less. But particularly we have seen that these converters also we can call as a non-linear load on the power system, because it takes a non-sinusoidal current and it requires a reactive power. And we have seen that because of the reactive power, efficiency of generators will less, transformer will be less, also the transmission line will be less, or voltage profile of transmission line will have a problems. So this is a one of the drawback that takes the reactive power from the supply. And what is other drawback of the converter? What is the other drawback of converter? Anybody can tell?
Injects harmonics in the source current.
Okay, it injects the harmonics into the grid or supply, and because of that, our grid voltage will be distorted, and this will affect the operation of sensitive equipments. And it is having another again the efficiency will decrease, and other disadvantages are also associated with the harmonic current. And now we want the converter. What should be ideal converter from power supply point of view? From power supply point of view, what will be ideal converter? What we expect? Converter should operate at what power factor?
1.
Converter should operate at unity power factor. That is first thing. And what type of current it should take from the supply?
Sinusoidal.
Sinusoidal. So our ideal requirement is our converter, AC-DC converter, should take a sinusoidal current from the supply and it operates at unity power factor. And for that, whatever we are having, that topic we are having is the PWM rectifiers. And that PWM rectifiers will work at unity power factor and take the sinusoidal current. Okay, so that is our intention. Why we are discussing these 3 lectures? To just trace the disadvantages of a thyristoride converter from power supply point of view, and we have traced these 2 disadvantages of the thyristoride converter. One is it works at the lagging power factor, it takes the reactive power from the supply. We see the reactive power taking from the grid is, we are having a lot of disadvantages. Also, converter is not taking a sinusoidal current from the supply. It takes the non-sinusoidal current from the supply, and because of that, we pollute the power supply system, and which will affect the other equipments. And we want to reduce this. Either we have to reduce the reactive power and harmonic current, and one of the another is we are going for increase the pulse number. Okay, that one, and that whatever other things we will discuss in the next lecture. So next lecture, particularly our next lecture is when we are having, I think on the 17th. Okay, 17th we are having now new timetable. It will be on the Tuesday at 10:15 a.m. Okay, is it okay? Tuesday we are having a lecture at 10:15 a.m. Any question? Any doubts? Hello? Am I audible?
Yes, sir.
Yes. So we'll meet on Tuesday, 17th of August. Okay. Thank you. Thank you.